Can you visualize a massive hydrogen superhighway spanning thousands of kilometers to deliver clean energy across a continent? Pipelines have moved oil and gas around the world, but can they do the same for hydrogen? Welcome to Titi Talks Energy, where we break down complex energy topics into clear, engaging, and insightful discussions. If you are passionate about the energy transition, make sure to like, subscribe, and turn on notifications so you don't miss the rest of this Hydrogen A to Z series. In today's video, we're exploring the concept of the hydrogen backbone, with a particular focus on the European hydrogen backbone, its vision, technical design, economic feasibility, and impact on the energy transition. Let's get right into it. When we think about the future of hydrogen, it's not enough to focus on production. We have to consider how to move it. Hydrogen can be produced in regions rich in solar, wind, and hydropower, but transporting it efficiently to industrial hubs hundreds or thousands of kilometers away is a major challenge. Europe's Repower EU plan targets over 20 million tons of hydrogen by 2030 to replace Russian natural gas. This raises the question: how do we deliver it to where it's needed the most? This is where the hydrogen backbone comes in. The European hydrogen backbone is a bold initiative by over 30 energy infrastructure companies across 28 countries, aiming to build a 58,000 kilometers hydrogen pipeline network by 2040. This backbone is a mix of new pipelines and repurposed natural gas infrastructure, forming a continent-wide hydrogen transport network to connect supply and demand across Europe, enable cost-effective decarbonization of industries like steel and chemicals, improve energy security, and support a competitive hydrogen market. The vision includes storage, import terminals, and infrastructure to provide system-wide flexibility and resilience. The backbone consists of 5 key corridors linking hydrogen production hotspots with demand centers. The first is North Africa and Southern Europe. North Africa has cheap solar energy, making it a perfect location for green hydrogen production. Pipelines could then send hydrogen north through Italy into Central Europe. Southwest Europe and North Africa. Spain and Portugal have vast renewable energy potential and can act as key exporters to Germany and Northern Europe in conjunction with underground storage sites available in France. The North Sea Corridor. This region has vast offshore wind and blue hydrogen resources. Hydrogen from the UK, Netherlands, Denmark, and Norway will be piped into Germany, the largest hydrogen market in Europe. Nordic and Baltic Corridor. This region has low-cost hydro and wind power. Hydrogen will be sent south into Poland and Germany. Eastern and Southeastern Corridor. This route connects Ukraine, Greece, Bulgaria, Romania, and Hungary with Central Europe, leveraging land availability for solar and wind. This corridor could provide a new energy security strategy for the region. Germany is at the center of it all as a part of every corridor within the European hydrogen backbone and is projected to be Europe's largest hydrogen consumer. We can see that the success of this network is heavily dependent on international and indeed intercontinental cooperation. This network is already having a ripple effect within the hydrogen industry. Recently, RWE signed a long-term green hydrogen offtake deal with Total Energies. Hydrogen will be produced in northwest Germany, transported via the German Hydrogen Core Network, which consists of dedicated hydrogen pipelines through the hydrogen backbone to Total Energies refinery in eastern Germany, which is Germany's largest chemical site. Now, let's look at the technical design and engineering challenges. Hydrogen pipelines pose different challenges than natural gas ones. A key issue here is material compatibility. Hydrogen embrittlement is a key driver. Small hydrogen molecules can diffuse into steel and cause cracking. High-strength steels used for natural gas are especially vulnerable. Pipelines also need coatings, different alloys, or plastic liners. Another challenge is pipeline condition. Existing defects, welds, and coatings must be evaluated using inline inspections and assessments. Pipelines may need pressure durating to reduce the risk of failure, which leads to hydrogen leaks. Speaking of leaks, we need to consider monitoring and detection. Crack detection technology may not be sensitive enough for hydrogen. Offshore and inaccessible pipelines pose extra challenges. In addition, we need to consider flow dynamics. Hydrogen's low energy density requires higher flow rates and compression pressures. This increases risks like erosion, especially in old and curved pipelines. Lastly, we need to think about blending versus pure hydrogen. Up to 20% of hydrogen blending in natural gas systems is possible. However, the European hydrogen backbone is designed for 100% hydrogen, essential for sectors like ammonia production, steel making, and heavy transport. This means that existing infrastructure must be upgraded to accommodate pure hydrogen. Backbone infrastructure components. The hydrogen backbone includes transmission pipelines that transport the gas from points of production to customers via large diameter high pressure pipes. Compressor stations are placed periodically along pipelines to control pressure drops and ensure that the hydrogen flow remains at the right pressure. Compressor sizing is key in order to achieve optimal results because compression costs are higher for hydrogen than natural gas. Compressing hydrogen consumes about 10 to 15% of its energy content. Next, we also have control valves, which enable safe daily operations and maintenance work. Gas metering stations are key equipment that are placed at entry and exit points and borders for the gas accounting, monitoring, and management. These are important because even minor flow measurement errors can result in large financial losses. We also have distribution stations which measure the gas and reduce the pressure from that of the transmission system to that of the distribution system, which operates at a lower pressure. Hydrogen purity and standardization. Hydrogen purity depends on the production method. For example, hydrogen produced by methane reforming is about 97 to 98% pure, while that produced by electrolysis is greater than 99%. So, to ensure interoperability, a common hydrogen purity specification is essential across Europe. Now, why is the hydrogen backbone a game changer? Number one, decarbonization. It enables hard-to-abate sectors such as steel, chemicals, and heavy transport to reduce emissions. It also provides scalable access to green hydrogen. The second is renewable integration. It stores excess energy from wind and solar as hydrogen and moves clean energy from where it's generated to where it's needed. The European hydrogen backbone is a game changer for the continent, but it is also a massive financial undertaking. Estimated capital expenditures range from 80 to 143 billion euros to build out hydrogen pipeline infrastructure across Europe by 2040. Interestingly, about 75% of this backbone is expected to come from retrofitted natural gas pipelines, reducing upfront costs. Still, retrofitting accounts for 50% of the total investment, reflecting the high cost of upgrades and new technology integration. A key hurdle is the investment recovery challenge. In regulated energy markets, infrastructure is typically financed through tariffs charged to end users, allowing transmission system operators, the TSOs, to recover costs over time. But in the early stages of the hydrogen economy, there simply are not enough users to make the pipeline operation profitable. The tariff level required to break even will far exceed what early adopters are willing or even able to pay. And so to bridge this gap, governments are stepping in. For instance, Germany has committed about 20 billion euros to develop its national hydrogen core grid by 2032. Public financing is essential here, not just for infrastructure, but to de-risk early private investments. Policy and regulation will be pivotal. To make hydrogen transport viable, we need standardization of hydrogen purity and pressure requirements so that we can have interoperability across borders. Subsidies and grants may be needed initially to attract private sector participation. And we also need clear regulatory frameworks that define how pipeline operators will be compensated, especially in the transition period before full market maturity. The levelized transport cost of hydrogen via pipelines is estimated at between 11 and 21 cents per kilogram per 1,000 kilometers, which adds less than 10% to the hydrogen production costs. This makes it a cost-effective option for large-scale transportation for continental distances. The economics are challenging but will be feasible with the right mix of public investment, policy support, and phased implementation that grows in demand. In summary, the hydrogen backbone is more than pipelines. It's a technical, economic, and political effort, one that could unlock hydrogen's full potential in Europe and beyond. So, what do you think? Could this be Europe's energy game changer? Let me know in the comments. And before you go, in the next video, we're diving into one of the most debated topics in the hydrogen world, the colors of hydrogen. From green to blue to pink, what do these colors really mean and why do they matter? You do not want to miss it. Don't forget to like, share, and subscribe for more deep dives into the various aspects of hydrogen in particular and the energy transition in general. I'll see you in the next video.